The outline would be explanation of introduction part, and then presenting the challenge and our solution. Then talk about the experimental works that we done. Then talk about the results and bring up some conclusion for the work, and then asking about your questions. So the role of photodetectors in the industry and sensors are they actually convert light into electrical signals. And they are essentials for many applications, for many sensor applications, like pulse oximeters and gas sensors. In specifically, the advantage of organic photodetectors we can say that they have tunable optoelectronic properties, and they present mechanical flexibility, lightweight design, and more after that, compatibility with large area fabrication stuff. So here is I bring here one of our recent journal papers, which was completely fabricated on the PET substrate, which is a flexible plastic substrate, and it shows both optoelectronic properties and the flexibility. The challenge that we have for the conventional bulk heterojunction OPDs, or organic photodetectors, is that I can start with here that a device of a photodiode, OPDs, have one anode material, normally ITO. Then we need to have a whole transport layer, and the active layer, or the layer that absorb light, includes a mixture of donor materials and acceptor materials. So then on top of that layer, we have a electron transport layer, which could be thermally deposited, or it could be spin coated. And then we need to have another layer of metal cathode with a different work function over the anode. But this is the conventional bulk heterojunction structure. They normally shows high dark current or low internal electric field, which is necessary for the self-power or zero bias performance. And therefore, we need applying external bias for sensing. The focus of this work is to solve this problem. Our solution actually emphasize to use two extra layers. One layer including the donor material with the more p doping concentration, and the other with the acceptor material and having more N-type doping in it. This addition of these two layers can enhance the internal electric fields with minimum charge transport barriers for charge extraction. This charge extraction is the heart of performance of a photodiode. And since we use the same material for the acceptor as what we have here in the active layer, and the same as donor for in the active layer, in the extra layer here. Here, there will be no addition of extra energy level barriers. So technically, it can help us to have a very good performance. To explain how this happened, this is a conventional device that we will have a depleted region around the active layer when we have only a mixture or bulk heterojunction. When we add two more layers, N layer and P layer, at the junction of these two layers, also some kind of depletion happen. So besides the intrinsic depletion region that we got for the bulk heterojunction, we add two artificial depleted region that they can increase the overall depleted region area, and it helps us for fully coverage of the size of active region. So to make a device, first of all, we need to use oxygen plasma for the glass substrate. We have a substrate of glass that there are ITO on top of it. So first we need to use the oxygen plasma to make it activated. Then in several spin coating steps, we will spin coating the copper thiocyanide as a whole transport layer, then the P layer, P3HD doped with the P dopant, then the active layer. Next, spin coat the N layer, and next the electron transport layer. And at the end, we can do the thermal evaporation of the aluminum as a cathode. This is the typical structure of our device. This is the glass substrate, and these are the active devices, which are AIDS devices of OPDs. First of all, we need to find out what kind of P and N layers we need to use in our structure. So what we did was to add the dopant materials. We select N-DMBI for the N-type dopant and the BCF as a P dopant. So we add a different amount of weight amount of dopants, and we saw that I mean, technically we expect that in different values of dopants, we have different carrier concentration. So we saw that after 10% of adding additional dopants, the carrier concentration start to plateau. And so we stop adding more. This was one of the criteria that we need to look at. Next one was to investigate the transmission, because in structure that we got, light enters from the glass and pass the different layers and goes to reach to the aluminum. So we need to have a high value of transmissivity. And we picked optimized thickness of these layers for each of the layers. To speak more, I can say that these are some of the results that I'm presenting here. The dark current of the photodiodes at zero bias shows 10 times improvement. And since we look at the dual wavelength sensitivity for both red and green, it shows that 3 times improvement in the photocurrent comparison for the new devices, and 4.4 for the red wavelength of the new devices. And the most important thing, I can say that the active layer thickness in the devices was 120 nanometer. When we use the Mott Schottky plot, we understood that based on this formula, we understood that the depletion width for the conventional device was 91.6 nanometer, and it was 127 for the new design device. And since this value is higher than the active layer thickness, we can say that our device is completely, our active layer is completely depleted in this new design. Overall, quickly speaking, we can say that we developed a design with adding doped extra layers, and it shows improvement in the performance in self-power mode. They have doping levels I pass on, and we design and optimize for the optical transmission of 90%. The dark current reduces by 10 times, and the green photocurrent increased 3 times, and the red photocurrent increased 4.3. The performance gains from the deeper electric field penetration that we got in the new design near the edge of the active layer. And at the end, this simple and scalable design can be used for further application. Thank you so much.